All right, Module 5. We're moving on. Module 5 starts on page 172 of 3rd edition. And you'll notice that the entire module is entitled Polyatomic Ions and Molecular Geometry. How'd I do?
Oh.
I said every word, okay. So the section 1 is polyatomic ions. This whole first half is about polyatomic ions. It's a big concept, but it actually covers very little material because it's directly related to what we've already learned about ionic molecules. Okay, so once you see the kind of the trick on this, or what we're the new aspect of the teaching point, it'll happen pretty quickly. The vast majority of the content that's going to be new in Module 5 is the molecular geometries. And I mentioned that when we were doing two-dimensional Lewis structures, that we're going to move into ways of showing molecules in 3 dimensions. And we'll be getting into that probably after a couple days on polyatomic ions. So we may get into that on Friday, since tomorrow's a short day. I'm actually excited about it because I get, like I said, I get to pull out all my little models that I have up there on the second shelf on the top. Little red, black balls and white balls glued together, connected with sticks. I get to get up here and play with things and maybe pass them around if you're gentle. Styrofoam is not like a very durable substance, okay? So better for maybe for me to handle them and show you than for me to pass them around, but we'll see about that. So we're going to pick up with polyatomic ions, section 1. And polyatomic ion, what is it? Again, this is in your book, it's in blue. They're ions which form when a group of atoms gain or lose electrons. When a group of atoms gains or loses electrons. So, big picture, here's what we're looking at. You know, in the last section, the last module, we looked at this ionic attraction. Okay? An ionic attraction, we have 2 atoms, let's say. And those atoms are a metal and a nonmetal. And so the metal wants to ionize and become positively charged, and the nonmetal wants to ionize by becoming negatively charged, by gaining electrons. And so the whole section on ionic compounds was based upon this principle that when you have something which has a positive charge and a negative charge in proximity to one another, what do? Yeah, they're attracted to one another. So they move close to each other and they form a molecule. And we said that this molecule that's formed technically doesn't have any bonding taking place, because in chemistry, a bond is when 2 electrons are shared. And that aspect of sharing means that neither one wants to give it up, and so when they hold on to those electrons tightly like that, without being willing to give them up, to us we call that a bond. You know, in your mind you may think of a bond as a physical connection. They're glued, like with the sticks, and we'll see those sticks, but again, remember, these are all forces. They don't represent actual physical attachment, but we call it a bond. In this case, there is no physical bond. There is no bonding taking place. There's a giving and taking of electrons to satisfy the octets, and then because of those net charges, they come together. For polyatomic ions, we kind of take this idea of 2 charges, or 2, in this case, 2 atoms that become 2 ions that are oppositely charged, and so they attract one another, and we extend that to this idea that we might have a molecule that has a charge. Okay? A molecule that has a net charge. In other words, a molecule which is an ion. So, just like we went through homonuclear diatomics, what does that mean? Right? The same nucleus, 2 atoms forming one molecule. In this case, this molecule which forms an ion we call a polyatomic ion. What does the word poly mean? Multiple or many. Okay. So a polyatomic ion is an ion which has multiple atoms that make it up. A polyatomic ion is itself a molecule. Okay? As a matter of fact, it's going to be a covalent molecule that has a net charge. We haven't done that so far. We've said when we make a molecule, we balance the charges, right? And to this point, every time we've made a molecule, we've made sure that the positives equal the negatives, and that is when we bring them together to form the net molecule. In this case, we're going to look at a situation where we have an element, let's say, that has a net positive charge, and it comes into proximity with a molecule, not an atom, a molecule that has a net negative charge. Now, just based upon the principle of charges, what would you expect to happen when that positively charged ion comes in proximity to this negative charged polyatomic ion? Same thing. They'll come together. And they'll form an ionic molecule. It's an ionic molecule because its existence as a net molecule is based on opposite charges attracting. However, within it, it contains a covalent molecule that is one of the ions. Okay? So conceptually, hopefully there's no problem with you saying positives and negatives attract one another and form an ionic bond to form an ionic molecule. And to this point, it's been an atom or an ion, usually it's a metal, or it will be a metal and a nonmetal that have opposite charges and are attracted to one another. So we're talking about atoms of elements. Now we're talking about atoms and molecules that attract one another. Okay, and we're going to be looking at this whole section 501 at what this hypothetical BC covalent molecule with a net charge looks like. They're the polyatomic ions. The most common polyatomic ion we're going to talk about is the hydroxide ion. Now, I show it whenever I write it in brackets, the OH with brackets around it. That's to let you know that this represents a structure within the structure. Remember, we looked at chemical formulas before, and I said, usually you're going to find all of your, it's kind of like in algebra, like terms get all pushed together. And so you're going to count up how many carbons, and you're going to have that subscript on the C, and so on. But I said there are times when we keep, within the chemical formula, we keep a nod towards, or we acknowledge that there's a structure within the structure. And we do that in the formula by using parentheses. And we do it within writing the ions, like we're going to be doing right now, by using brackets. So we're looking at the hydroxide ion. The hydroxide ion has a net 1 negative charge. So what does this look like? Go ahead and draw using a marker for a bit here, and then we'll cover it over. Let's go ahead and do the Lewis structures for hydrogen and oxygen. Okay? Lewis for hydrogen is what? How many? It just has one, right? One valence electron. We're assuming we're going to be making a covalent molecule, right? Because I said the polyatomics are all covalent molecules, which means there's going to be at least one covalent bond between these two atoms. Right? So when we draw the 1 here, that's brown. Can't do brown. Got to go black. Here we go. So hydrogen has the 1 valence electron. Oxygen, we have pair, pair, single, single. Is that correct? Okay, so column 6A element, 6 valence electrons, that's the structure. And we said that it's going to have 1 bond, right, to make it a molecule. Now let's look at the charges. Let's look at how many valence electrons each molecule sees. How many does hydrogen see? 2. How many does oxygen see? 7. Right? How many does hydrogen want to see? Well, how many does hydrogen want to see? 2, and sees 2. How many does oxygen want to see? 8. How many does it see? 7. Right now, what's the net charge on this molecule? Let's think about it. We haven't added or taken away anything, right? So since there were 2 neutral atoms before and we bonded them together, we haven't added or subtracted protons, we haven't added or subtracted electrons. What's the net charge? Neutral. Good. It's neutral. However, hydrogen is satisfied, but oxygen is not. what would be required for oxygen to satisfy its octet? Go ahead. One more electron, right? So the net charge is 0 right now. When this molecule has a fully satisfied valence electron for both, or for all of the atoms involved, it would require another electron. And when it acquires that additional electron, what will its net charge be? 1 negative, correct. 1 negative. Its charge becomes 1 negative. When it's at 1 negative, is hydrogen satisfied? Yes. Is oxygen satisfied? Yes. And so that's why when we're talking about the OH or hydroxide polyatomic ion, we draw this structure. It's a hydrogen with a single bond to oxygen, with oxygen's octet full, meaning we had to acquire 1 additional electron to make it satisfied, producing a net negative 1 charge. Now, the question is, with this structure, where is the negative 1? Is it on the hydrogen? Is it on the oxygen? I want you to think of it this way. It's not necessarily on the hydrogen or the oxygen, because we're going to do ionic bonding. It's on the molecule. The molecule has a net 1 negative charge. If we had to ascribe it somewhere, we would say yes, that 1 negative is towards the oxygen because it's the one that received the 1 additional negative. Matter of fact, we do the next couple, we're going to actually detail where the negative charges are at. But we're going to look at the net molecule and say this net molecule has a charge of 1 negative. Okay. There is no such thing as a hydroxide molecule, technically speaking. If I say hydroxide molecule, that kind of connotates or gives the idea that it's a net neutral charge. There is a hydroxide ion. Okay? And if somebody says a hydroxide molecule, don't go, technically no. Well, yeah, that's true, technically no, but don't be weird about it, okay? Just remember, there's no such thing as a net neutral hydroxide molecule. It's a 1 negative hydroxide ion, polyatomic ion. And a polyatomic ion is just an ion that within itself, it's a structure of more than 1 atom. Okay. Now, if I try to make a molecule with this, what kind of molecule is it going to form? An ionic molecule, right? Because it's a charged molecule. So we get to making sodium hydroxide. We're going to see a lot of sodium hydroxide. But we know now that sodium is a column 1A element. So when sodium ionizes, it becomes a +1 ion. And when I have a -1 hydroxide ion in proximity, what are they going to do? They're going to come together, right? They're going to, just as we said before, we had a positive charged A molecule and a negatively charged BC molecule. They're going to come together. And in the same way, sodium hydroxide is an ionic molecule that is the ionic attraction between a sodium ion and a hydroxide molecule. But the chemical formula is NaOH. Technically, right now I'm showing you with brackets, but soon I'm going to show you that I'm going to start putting in parentheses, okay? Just so we get the terminologies right. But for now, I want you to see that what's in brackets is the polyatomic ion portion. So if sodium has a +1 and hydroxide has a -1, if we were to do the formula, we just use the same thing we did before. Drop the charges and use the numbers. It's a 1 and a 1, which means we don't write it, and it's sodium hydroxide. Second ion we're going to use, just because it's a little more fun, is the carbonate ion. Carbonate is a molecule, and these are all listed, just so you know. These are on table 5.1 on page 175, okay? So you have table 5.1 that lists the molecules that you are going to have to memorize. Table 5.1, it's another one of those sorry, you've got to memorize the names and the formulas. Do not memorize the Lewis structures. They don't need to do that, okay? Just the names and the formulas, including the charges. It's key. All right, so we'll go back to this molecule here, the carbonate ion. To give us a head start, because of symmetry, what do you think this is going to look like? Just from symmetry purposes. Go ahead.
Carbon in the middle with an oxygen at the bottom.
Okay, so carbon in the center with 3 oxygens around it. And now that we're pressing in towards 3-dimensional, we're going to separate all 3 of those equally by 120 degrees. Rather than putting them at the quadrants, we're going to separate them by 120 degrees. Okay, so let's start with this. Now, let's go through and do the Lewis structures for each one of these atoms. Remember by now that carbon is a column 4A element. We're going to put 1 on each of the cardinal positions. Oxygens, 6, and oxygen 6. And all I'm doing is giving a single towards the connections, okay? And we know that since it's a molecule, there's at least 1 single bond between all of them, right? So let's go ahead and do the singles. There's a single bond, and there's a single bond, and let's say that, well, okay, there's a single bond, okay? Now, this is a smudge on the board, so don't think that's an electron, okay? And there's no I like in silicon here, so it gets mixed up either. So, is anybody satisfied right now? No, nobody's satisfied. So I'm going to go ahead and choose to start from the top. Let's see if we can help this oxygen out. What does that oxygen need? Right, 1 more. If I bring this extra valence electron up here and bring this one down here, I can form a double bond, right? Okay, now, just for consistency, let me go ahead and reorient these like that. Do you see now that these are all divided by 120 degrees as well? A set, 120 degrees each. Okay. What else can I do? Carbon has no more to give, right? And carbon is satisfied. The top oxygen, is it satisfied? Yes. The bottom 2 oxygens, are they satisfied? No. In order for the bottom 2 oxygens to become satisfied, what do they need?
8.
They need 8, and they have, so they each need 1 more electron. If I add 1 more over here, and I add 1 more over here, are they satisfied? But I went from a net neutral to a net 2 negative. Do you see that? I added 2 electrons to complete their valence. To satisfy those 2 oxygens, I had to add 2 electrons. And since I was a net neutral, by adding 2, the entire molecule now takes on a 2 negative charge. Now, you would not be required to draw this molecule as a Lewis structure, but you will need to know that if you're forming something with a carbonate, that it is a CO3 2 negative ion. Okay, its formula is CO3 and its net charge is 2 negative. And just have it memorized, and that's all on table 5.1. All right? So, a little bit more professional than our dots and lines up here. It looks like this. Where there actually is a negative, if you will, we had to create a -1 on this oxygen and a -1 on that oxygen in order to satisfy their octets. And so this is trying to represent that this molecule has a double bonded 2 single bonds, and those oxygens that have the single bonds each have a net 1 negative charge, so the entire molecule now takes on a 2 negative charge. But again, you would be asked for something that's made with a carbonate, and you would need to know that that's a CO3 molecule that has a 2 negative charge. Or if given a CO3, you would need to tell me it's a carbonate and it has a 2 negative charge. So on table 5.1, oh, excuse me, 1 more. So this is using this carbonate to make an ion. potassium carbonate. So potassium is K. There's a carbonate molecule. Potassium has a charge of 1 positive, right? When potassium ionizes, it's a column 1A element. It takes on a +1 charge. And carbonate, this should be a subscript 3. Again, this is frustrating that PowerPoint keeps changing my subscripts and superscripts. But that's a carbonate, should be a subscript 3 with a 2 negative charge. If I have a potassium with a 1 positive and a carbonate with a 2 negative, how do I balance those charges? I'm going to need 2 of these so that I have a total of 2 positive to balance out the 1, 2 negative. And we're going to show this, we can show this, if we were doing Lewis structures, by putting those positive potassium ions near the negative oxygen ions. However, don't think about it as potassium bonding with that oxygen. I want you to think of it as 2 potassiums bonding with the entire carbonate molecule. Okay, that's the key thing I want you to carry away from this. So, as I said on table 5.1, you need to memorize the names, the formulas, and the charges. And you'll see why in a minute, so you go ahead and keep that table open. In addition to just memorizing them, there's a few helpful hints, some things to remember. You're going to notice that there are ions in here which end in oxygen. A lot of them do. Look down the formula columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them end in oxygens in the formulas. And if they end in an oxygen, their name ends with an ate or an ite. Just like we had ide, like fluoride is the ionic name for fluorine. In the same way, when we get the polyatomic ions, if the formula, the proper formula, ends in an oxygen, its name is going to end with either an ate or an ite. So chlorate, chlorite, nitrate, nitrite, carbonate, chromate, sulfate, sulfite, okay? And phosphate. You should know that every one of those names, the last molecule, or excuse me, the last atom in the appropriate molecular formula is going to be an oxygen. You also notice that there are a few of them where they're very similar. They have the same basic name, but they use ate and ite. They change back and forth. Again, chlorate, chlorite, nitrate, nitrite, sulfate, sulfite. What's the difference there? Well, for those pairs, the one that has more oxygen is going to be the ate. Its name is going to end in ate. And that one which has less oxygen is going to end in ite. The examples I give here are chlorate and chlorite. See, it doesn't say how many oxygens, it just says more or less. In this case, the chlorite has 2 oxygens, and the chlorate has 3. Since ClO3 has more oxygens, it gets the ate ending. And ClO2 has fewer, therefore it gets the ite ending. All right, so it's not because it has 3 or 2, it's because it has more or less than its pair. So, and again, looking at that, the first atom in both of these formulas is a chlorine, right? Chlor starts, that'll give you the hint on how to start. So the atom name for the lead atom is chlorine. It has more oxygens than the other. It's an 8, so it's chlorate. The lesser, chlorite. Okay, so oxygens end in ate or ite. If there's a pair, the more oxygen ends in ate, the lesser ends in ite. And the only positively charged polyatomic ion that you have is ammonium. On your chart, it's the very first one listed, upper left-hand corner, ammonium. It's an NH4 plus 1 polyatomic ion. It's the only positively charged polyatomic ion you're going to have to memorize. Now, because this is such a common requirement for people to memorize all these polyatomic ions, if you were to Google this or look it up on YouTube, there are lots of little songs and ditties that you can learn, raps and all kinds of different mnemonic devices to memorize these. So if you want to go ahead and in your own mind memorize it, just during the exam, keep the singing to a minimum, okay? But whatever works for you. Now, a lot of these lists of polyatomic ions from other chemistry courses include more or less than these. So if you choose to take one of those standards, you may be learning more than you need to, but if it helps you, then use it, okay? It's a mnemonic device. Some people, they can't say their ABCs without singing it. It's always A, B, C, D, E, F, G, you know? Now, you know, of course, if you get stopped by a police officer and you think they're being funny when they say to say your ABCs, you know, for the sobriety check, only drunk people sing to the cop, okay? That's what they're checking. So if you sing to the cop, you're drunk. Because what person's going to go A, B, C, D, E, F, G? They're going to look at the officer and go A, B, C, D, right? So if you sing, your inhibitions are low, gotcha, okay? So in chemistry, if you start singing away those polyatomic ion songs, that's not anything about your sobriety. I'm just saying, you know, if that's what you need to do to learn it, that's fine. Just keep the singing to a minimum in class. Either that or come up with your own for this class that only includes the ones that we have. Maybe that'll be an extra credit. Come up with a song or other mnemonic device to memorize Table 5.1. We'll think about doing that. So this brings us up to example 5.1. First part. What is the chemical formula for calcium nitrate? Okay, calcium nitrate. Now, let's pretend that nitrate is an atom. It's just another atom. Okay, so we just haven't learned this one before. Now we're pretending it's not an atom, it's a molecule. But for right now, just think of nitrate as another atom. Now, if we were doing an ionic bond between two atoms, what would be the first question I would ask you? What's our process, our pattern? Do you remember? We've done a bazillion of these, technical term, a bazillion of them, right? And so every time we've had to form an ionic molecule, I've started by asking you, what are the atoms involved? What are the elements involved? You'd say, oh, it's easy. It's a calcium, and it's this nitrate atom thing, right? It's a molecule, but this nitrate, okay? Now, you need to already know that a nitrate doesn't start neutral. The atoms start neutral in our process. This nitrate molecule is actually a nitrate ion, a polyatomic ion, and it starts with a -1 charge. So we've already got the first and second question answered. What are the atoms in play? Then what are the ions in play? Calcium is a column 2A element, so it takes on a +2 charge. We've already said that nitrate in itself is not neutral. It is a polyatomic ion and has a -1 charge. Question to you is, what is the chemical formula for calcium nitrate based upon those charges?
CH positive, bracket, NO3, negative.
Okay, let's just go back to process. We drop the charges and transpose as subscripts the superscripts, right? So, calcium nitrate, what would be the subscript of calcium in the formula? There's no negative or positives. 1, but we don't write 1s, do we? Okay, so it's going to be calcium. What is going to be the subscript on the nitrate? 2. We drop the charge and bring that down as a subscript, and we write it this way. Calcium nitrate. And checking it the same way we did before, I have one calcium ion with a +2 charge, and that should balance out 2 nitrate ions, each with a -1 charge. And do they? 1 times 2 equals 2 times 1. Is that true? If that's true, then the formula is correct. Here is kind of one of the things you need to be able to do when you see a molecule like this. If I ask you the question, how many calcium atoms are in this molecule? How many calciums do I need? If I had building blocks of each of these elements, how many calciums would I need? Yeah, just 1. Right? How many calciums do you see represented up here? We can count up the calciums by looking at the element, calcium, right? And then looking for its subscript. What is the subscript here? It's an implied 1. So how many? 1. Here's where it gets a little bit tricky. Let me ask this question this way. How many nitrate molecules are in this molecule. Just listening to the fluorescent lights hum. How many nitrate molecules? How many nitrate polyatomic ions? Two of them, right? You see the subscript 2? Do you see the parentheses saying nitrate? Nitrates within the parentheses? How many nitrates do I have? 2 of them. How do I know? Because that's the number 2, right? You're all comfortable. This is the number 1. This is the number 2. This is the number 3. Do I need to go any farther? Okay. So the pattern is, the number is how many? How many calciums? Not 1, but 1. How many nitrates? It's not 2. It's 2. Right? Now, let me ask it another way. How many nitrogens are in this molecule? I've heard 3 different answers so far. The only number I haven't heard yet from the 4 we practiced was 4. Okay? How many, if I had to build this out of building blocks, how many nitrogens would I need? Well, to make 1 nitrate polyatomic ion, I would need 1 nitrogen. How many polyatomic ions of nitrogen do I have? 2. 2 times 1 is 2. There are 2 nitrogens up here. Do you see that? Because this subscript is a multiplier for every subscript inside. I have 2 nitrate ions. Each one of those has 1 nitrogen in it. Therefore, total, I have 2 altogether. Now, bonus round. How many oxygens are in this molecule? 6. Good. Thank you. There were no 6. It's 6. There are 6. How do I know? I have 2 of these, and every one of these has 3. 2 times 3 is 6. We're beyond what we rehearsed. I know. 4, 5, 6. There. We covered them all. There are 6 oxygens. There is 1 calcium. There are 2 nitrates. And within those 2 nitrates, there are 2 nitrogens and 6 oxygens. Does everybody see that? Okay? And I'm not really being sarcastic. I'm using this as a, hopefully you're going, okay, duh, I get it now. This is just something you got to see. You got to see that I've got 2 nitrates, and that each nitrate has 1 nitrogen and 3 oxygens respectively. So total in this molecule, I have 1 calcium, 2 nitrogens, and 6 oxygens. So let's do magnesium phosphate. What are the 2, well, let me see. Did I reduce it down? No, I didn't. All right. What are the 2, quote, air quote, atoms at play?
Magnesium and then phosphorus and oxygen.
Okay, but we're going to, for our purposes, I'm trying to keep the same pattern before, that it's just going to be magnesium and phosphate, right? Because phosphate, we know, we're not going to break down phosphate into its elements. When I ask what are the atoms at play or the elements at play, right now we're kind of forcing it into our old paradigm. I won't be saying that's the whole time. I'm just trying to make you see, oh, it's the same as we did before. It was easy before, so guess what? This is easy too. There's nothing magic here other than it looks hard because I've got numbers that are bigger than 3. Okay, we have magnesium and phosphate are in play. What are the ionic charges of these 2? When magnesium becomes an ion, it takes on a 2 positive charge, right? Magnesium, column 2A, row 3, 2 valence electrons. Metal, when it sheds those 2 electrons, it becomes a +2 ion, or 2+ ion. Phosphate, we've already memorized from table 5.1, has a 3 negative charge. So, what is the formula for magnesium phosphate? Magnesium phosphate. Is this radically different than anything that was so easy 2 days ago? No. Other than it's got lots more numbers and brackets in it, right? But the concept is exactly the same. What is the subscript of magnesium going to be? It's going to be a 3. Not a 3, but it's a 3, right? Yes, it is going to be a 3. And what is the subscript of phosphate going to be? 2. Where did you do that black magic from? Where did you get those secret answers? Right here. Drop the signs, transpose them as subscripts. No magic. You know, it's just the same thing we've done for the last couple of weeks. It just looks a little different because now we've got a couple of elements in brackets. But you're treating this whole thing as one thing. It is a covalent molecule that has a net charge of 3 negative. Okay? But it's just one thing. It's one piece. It's like rather than having one block and one block and one block, I now have one block and another structure that already has 5 blocks in it. 1 phosphorus and 4 oxygens. They're all stuck together. So that rather than bringing one Lego and one Lego to form a molecule, I've got 1 Lego and 5 Legos that are already stuck together, coming together. And they come together in this formula. Magnesium phosphate. Now, how many different combinations of magnesium and phosphate can we have? How many different formulas that involve magnesium and phosphate? Okay, let's back it up. For an ionic molecule, how many different formulas can there be? Just one, right? If they come in greater combinations, we know that we can reduce it down. Take the greatest common factor within the subscripts and reduce it down, reduce it down. There's only one. That's why we can call it with the "ide" ending. The metal name, the nonmetal "ide" name. There's only one way that they can work to have a net neutral charge. In this case, the phosphate is one of the ions, magnesium is the other ion, and they can only come together at a certain combination. And the combination for magnesium phosphate is Mg3PO4 scrub 2. Now let's walk through this relatively quick. Question?
I was going to ask, does it matter if you put brackets or parentheses?
This is going to be the standard, parentheses. I'm showing you brackets now so you can start to see that that's a substructure. But when we write it out as a formula, it's going to be in parentheses. So, the question, of course, then is, well, let's first check the charges. I have 3 magnesiums at +2, and that needs to balance 2 phosphates at -3. Is that true? It's true. So our formula is correct. Now, how many magnesiums are in this molecule? I almost heard you, but I don't think you're right. So say it again boldly and be wrong boldly. Good. Nice try. Play next contestant. 3. How do I know how many magnesiums there are? It says 3. Okay. Want to try again? How many phosphates are there? No. There's 2 because it says 2. There's 3 of these and 2 of these. Trying to get the magic to transmit to you. There's a pattern there. Do you get the pattern? You read the number, okay? 3 magnesiums and 2 phosphates. Okay, now we'll get to the harder questions that involve multiplying single-digit numbers. So I know first grade's working on this, so we as a class of juniors can do this. Here we go. Okay, how many phosphorus are in this molecule? Come on. Oh, don't stop because you got them wrong. Get the hard one right and wipe away all that easy error, okay? Now, how many phosphorus do you see up here in that molecule? The way it's written right here. If I were building this with Legos and one of those Legos was phosphorus, how many phosphorus Legos would I need to build this? Thank you. 2. There are 2 phosphorus. How do I know? Well, each phosphate has 1, and I have 2 of them. And 2 times 1 is 2. Now the hard one.
Oh.
How many oxygens do I need to build this molecule? 8. How do you know that? How do you know this dark magic? Right? What's the dark magic between the answer 8? 4 times 2 is 8. All right. So 3 magnesiums combined with 2 phosphates. And the 2 phosphates, each one is made up of 1 phosphorus and 4 oxygens. So for 2 of them, I have 2 phosphorus and 8 oxygens to make 2 phosphate ions, which combine with magnesium in a 3:2 ratio. Okay. Oh man, it just keeps getting the same. It's the same as we did last module. It's just one little piece different. It's the rather than having an atom, you're having a molecule that has a net charge. So copper 1 acetate. What are the atoms in play, the elements in play? Well, it's copper, right? And there's your acetate molecule because you have it memorized from table 5.1. And you know that acetate has a 1 negative charge, but what does copper have? What kind of charge does copper have? It's a deep, dark secret on the charge of that copper ion, isn't it? I mean, it's beyond the ability of the typical junior to figure out what should that charge be, since it's a transition metal. I mean, you think they'd give us a clue. It's like around here, you're following cars in Louisville. You wish they had some way when you're following a car that you could predict when they're going to turn. There's got to be a way that we can know that when we're behind a car. And why is it when they use that thing, even when they're at a crossing guard and they come up to the school, they don't have it on until the crossing guard calls them forward, and then they turn on the turn signal? Like when there's no turn for like a mile before that left-hand turn, they suspect that if they used it in advance, I would think they're going to turn into the field. But I assume they're going to wait till the next left turn. But then it throws off the crossing guard, and then you got to sit through another cycle waiting for the other direction to stop. If only there was a directional prophetic device to let me know what they were going to do, right? If only there was some way that I would know what this transitional metal known as copper, what charge it's going to have. I'd be so grateful. Wouldn't you be grateful for that? Is there such a predictor? Yes, there is. And who knows the secret of this dark magic of what the charge of this copper ion is going to be? Yeah, +1. How do we know? Because they told us right there. Okay? It's a +1. And we know that acetate is a -1, right? So we need to now drop the signs and look at the superscripts, which are both 1, and we need to transpose them as subscripts. But since we don't write the 1s, we just write it like that. Copper 1 acetate. If it was copper 2 acetate, it'd be C2H3O2 sub 2. But it's not. We just have one of them. Oh, but here is where we start to have fun. Because since there's only one of these, guess what? Boom, we don't need the brackets, or we don't need the parentheses. There's only one of them. So CuC2H3O2, copper 1 acetate. Well, let's check it out. Let's check the charges. That's not right. That didn't get updated. But let's do it live. Copper, 1, charge of 1. 1 times 1 is 1. You got that wrong. Okay. And acetate, all of this. We have 1 of all of this. And that has a charge of -1. 1 times 1 is 1. Does 1 equal 1? Yes, it does. The formula is correct.